My name is Eliot Miranda. My colleague Clément Béra, been a long-time Smalltalk implementer. I was here in 2003 giving a presentation in the same course on the system that we're describing now, which at the time was an architecture in my head, something that I hoped to implement. And in fact, it's been these 13 years that it's taken for me to find collaborators and space to actually complete the project and get to a stage where I can deliver on the vision that I had then. You might think that those 13 years were long enough in which a project might become completely irrelevant and be discarded, but it has not been the case. So, you know, follow your dream and never give up, and you may get to realize it. We are in the business of making it efficient to run dynamic languages. Dynamic languages, all the rage right now. You almost certainly use JavaScript in your daily work as a student, and adding behavior to web pages, etc. This is an example in Smalltalk, and it simply sums the elements of a collection. And so it's an abstract method that sits at the top of a collection hierarchy, and it's inherited by a lot of different concrete collection classes. The first thing you see is that there's no types, and we initialize a variable with the integer 0, and we don't bother to declare sum or anything like that. We can just assign it. And the second thing, you see these square brackets around the colon element. Sum becomes equal to sum plus element, close bracket, is a closure. So we create a code closure, and we provide that as an argument to an iterator message do, and we ask the receiver to apply that closure to all of its elements. And each of the many subclasses of the collection abstract class may indeed implement do in its own particular way, depending on its interior representation. It might be a hash table with keys that are key value pairs, and we need to iterate over that hash table. It might be a flat array where we can use integer indexes. It might be a computed interval from one start value to another, and we don't know when the do is written what do will be executed. So what you can see here is very concise code, but very generic code, and code that's been factored into lots of small methods. So one of the problems that dynamic languages pose to the implementer is that we have very little scope for optimization. Another more important is that we've got lots and lots of calls, even in doing something simple like iterating over an array, where in a standard procedural language the compiler would be able to reduce everything to machine instructions. Here there's no scope to find, there's very limited scope to find machine instructions. In fact, there's a lot of abstraction here. But one of the lovely conveniences that we have in dynamic languages is that, you know, sitting there looking at this, I could add another optimization. I could add another implementation of sum in a subclass. And so here's sum in a subclass which assumes that its instances are indexable with the integer indices from 1 to self-size. We don't know how self-size is implemented, but we're assuming that we've got a to-do method which takes the integers and which will sum by using an indexing operator at, again a dynamically bound send, which is going to find the element associated with at. And it's really nice that I could just sit there and add that. But that's a real problem for the execution system. The execution system is dealing with dynamically bound sends all the way through its execution. So how is it? How is it that these things are typically executed? We typically have a heap which is full of objects, some of which is code, and we have some components like a memory manager and an execution engine, which might be an interpreter, and some primitive operations. And the interpreter's job is to interpret that dynamic code. And of course, the experience is that the system is too slow, and that what we need to do is to add some form of compilation. If we add ahead of time compilation, we're going to lose all of our dynamic advantages. So we need a just-in-time compiler that will compile the code on demand, because that's a really nice way of dealing with the ability to add code to the system and modify code to the system. So then we can think of the VM architecture as a heap of objects, some zone in which the JIT produces code. It might be interspersed in the heap, but in the systems that I've been working with, it's always in its own area. And the execution engine is now a hybrid one that it can interpret and it can compile. One of the issues you have in JITting is if you think about a method which is interpreted only once. Let's say some method that was interpreted at startup. It's much more expensive to JIT, which is essentially an interpretation over the code with the side effects that you produce the machine code and concatenate the machine code for the operations concerned. And so you might actually benefit from being able to avoid JITting until you might execute a method for a second time. So there are actually advantages to having this mixed context. So that's the architecture of the Smalltalk virtual machines that I'm going to be discussing today, and similar to a number of other executions. So going back to that example of the indexing via @ in our second sum call, how could it be that we can improve performance, avoiding the cost of every time we send a message, figuring out what code is to be executed? Well, in the 80s, Peter Deutsch, with the Smalltalk virtual machine done at Xerox PARC, invented the inline caching technique. So imagine that my method is compiled to a bytecoded language, and there are bytecodes which represent things like pushing the receiver, pushing an instance variable, etc., and bytecode for making a particular send. So what I'm considering here is the compilation of the send instruction for the @ message that we send to whatever self is. And the JIT compiler generates a 2-instruction sequence for this, and it loads a register. Here I've got RCX, which I'm using as a mnemonic for class. It loads a register with the address, effectively, of the symbol that names the @ procedure call, and then it calls some runtime routine in the VM. And if that code was ever to be executed, then what that runtime routine would do would be using some other register which has the self in it, that we haven't shown how the compilers reference self, but it'll look up the message @ in whatever the class of self is, and in this case I'm imagining that it's an array, and it will find some bytecoded method, and associated with the bytecoded method, it may find some machine code method, and if there's no machine code method, it'll actually have to create one. So what it can do is have in its hand the machine code form for the array @ method, which would actually index the array. And to optimize sending, it's going to modify the original 2-instruction sequence. So now, instead of loading the register with the name of the procedure, we load the register with the class of the object which received the message. In this case, it's an array. So what we have is a load of the class array into this register, and we're going to call an entry point in the machine code. And when we do this on first execution, the compiler will jump to the body of the method, and execution will continue. But the second time around, what will happen is that we'll execute these instructions. So now RCX will have an array, and we'll go to the entry point of the array method. And what that will do is, given that self is in a dedicated register, it will find out the class of self, which is the class of self at this send, not the send at the time when we compiled. And it simply compares the two. And if the two are the same, then execution continues. Now we've reduced some kind of hash lookup where we're associating some class and some selector with a method with a very simple fetch the class of an object and compare it against a constant and continue. So this is a lot quicker, and this was the technique that Peter Deutsch developed in the 80s that gave us the first efficient Smalltalk machines on commodity hardware. It was on 68,000 processors. So then the question comes, well, okay, what happens if I add some polymorphism into the system? So here what I've got is I've got the array 1, 2, 3. That's hash parenthesis 1, 2, 3 close parenthesis is literal notation, Smalltalk's literal notation for an array, which has 3 elements in it. But the second one, 1 to 3, is effectively equivalent, but it's quite different. It's an interval, so it has a start and a stop and a step, right? And so it implements at in a completely different way. It implements at by doing some arithmetic, right? It multiplies the step by the index and adds it to the start. So if I was to evaluate that in my collection, it turns out that in my library on the first slide, it turns out that these are both sequenceable collections, so they would both inherit this second method, right? And when we came to execute that at here, this send comparison that we've generated here would fail. So what happens when it fails? What we do then is have the failure path in the method call into the runtime and now locate the new class and create a little table, a little dispatch table in machine code on the fly to invoke the original method and invoke the new method. And we call that a polymorphic inline cache. The first thing is called an inline cache. It caches one message lookup. And what we're going to do is produce some simple lookup table that will deal with some degree of polymorphism. And typically it's convenient, right, in the JIT to decide how big this table is, and you initially fill it in with two elements and you allow it to grow to some number, for example, like 6. And then if you get to megamorphic sends, you have to use another strategy. But we're not going to discuss those strategies today. I just wanted to give you this example. So when we execute this in the context of the interval, the 1 to 3 sum, we're going to get a failure. And we're going to call once we've rebound, we're going to call this pick, and this pick just does a series of comparisons. So the first entry compares the current class against array and jumps to the no check entry point, which will execute the code, and the second case checks for interval and so on. And this is stretchy, so it might be able to expand to some number of cases. So that's great, and it turns out that if you look at Smalltalk VMs which don't have polymorphic inline caches, they spend a large percentage of their execute time, for example, like 50% of entire execution, rebinding these entries as the number of classes changes. It turns out that sort of 90% of the sends in a program have only one class, but this remaining 10% are extremely expensive to deal with because they're failing all of the time. And when you replace with this nice table technique, you get rid of that overhead and get a substantial speed up. Well, okay, so now we're in the 90s, and the team at Self and indeed at Stanford under Dave Unger were dealing with a language which was even more difficult to optimize than Smalltalk Self, which is prototype-based. And because it's prototype-based, there's even more polymorphism because individual objects have their own methods instead of objects being members of classes. And they were struggling to produce an efficient execution engine using conventional compiler technology and type inference, and were failing. And so they went this route and added picks as a way of dealing with the higher degree of polymorphism. But then they realized this collects type information. So associated with every send that has been executed in the program, we have either a monomorphic cache which says, for this send location, we only ever had one type of receiver, or for the other megamorphic, polymorphic sends, we know the set of classes that we've seen so far. And that's information which is perfect for an optimizing compiler to use. The only problem about it is that it is speculative. It tells you what happened in the past. It doesn't tell you what happened in the future. We'll discuss that soon. So the thing that we need to do is to use that information for an optimizing compiler. But if we willy-nilly optimize our code, our dynamic performance is going to suffer because we're going to spend all of this time optimizing code aggressively. So what we need to do is find some way of only optimizing when appropriate. And most programs observe this pattern of 90% of the time is in 10% of the code, or 95% of the time is in 5% of the code. So if we decorate our machine code produced by our first level JIT with counters, and we can make those counters affordable, what we can do is allow those counters to identify the hot spots, as they were called in the first Java VM, the hot spots in the program that would profit from optimization. So we modify our baseline JIT to put in counters. Now in our system, and in a number of Java systems, we count conditional branches. You could count every message send, every method activation, but that's rather expensive. It turns out that in typical Smalltalk programs, conditional branches are about 6 times less frequent. So counting conditional branches is a much better, cheaper technique of finding hotspots, but it also gives a nice ability to, but we haven't exploited that ability yet, but we'd like to, of having the counter being able to tell you how many times you've encountered the conditional branch and how many times you took the conditional branch, so you can get basic block counts and know what is the common path. So then, what happens in these VMs, and I should say that Hotspot was the first commercially available VM that used this technique. It was available in 1999 and has evolved successively since then, and that's the Sun Hotspot, now the Oracle Hotspot VM for Java. But you see similar techniques in the Chrome JavaScript VM, which is called V8. In the WebKit, which is the Apple VM for Chrome, and in a number of other dynamic languages. So what happens is that when a counter trips, there's some kind of pause, and we invoke an optimizer. And in this diagram, I'm writing the optimize as a black box, because optimize is typically in the VM. It's actually in the VM with the rest of the runtime, so it's part of that lower level, and it's implemented in C++, and I can't see it from the top. And then what the optimizer does is generate some machine code. In fact, what it does is analyze the stack and try and inline a whole series of the bytecoded methods, and I've drawn my bytecoded methods on the left. Inline those bytecoded methods to produce some much bigger machine code method, which covers essentially a large portion of the call graph. And by inlining a large portion of the call graph, we now have much more opportunity to optimize using conventional techniques. And of course, inlining has avoided all of those call overheads. But the problem is that the code is still dynamic, and we could still introduce new types into the program. So what we do is put guards in the machine code at the start of each basic block, which makes assumptions as to the types that it's inlined, and those guards must be passed, must verify that the classes are as expected, and if those guards fail, then we have to do something else, and we have to do this hairy thing of de-optimizing the optimized code so that the stack is now reverted to its unoptimized case, and let the system run again. And then when the counters trip again, we will re-optimize in the presence of the new type information. So there's this kind of big cycle. Okay, so that's great, but I don't like C++. I've never enjoyed using it, and I'm a Smalltalk guy, and Smalltalk's kind of different. You saw the language doesn't even have curly brackets, it's got square brackets. It doesn't even look like JavaScript. But how is it different? Well, the real difference is that Smalltalk is self-representing. So methods and classes are first-class objects like any other. Like those arrays, etc. And there's code in the system which define the behavior of classes, and code in the system which defines the behavior of methods and how to create them, etc. And so the implication of this is really nice. The compiler, the source code compiler that takes Smalltalk source code, produces bytecoded methods, and it is a Smalltalk program, and you can, if you want, modify the compiler while you're working on your project. You might want to insert some strange code to monitor the use of your instance variables, or whatever you might want to do. You can do that. So let me go. Yeah, that's right. But Smalltalk takes things to not to extremes, but to a point of consistency, so that we have a minimal number of concepts to consider. And one of the things that it does is represent activation records as objects too. Now, an activation record, what's an activation record? An activation record is that which records the state of a method activation or a procedure activation. So it's, where am I in the current method? What's my PC? What are the values of my arguments and my local variables? And where do I have to return if I have to return a result? So having activation records as objects has a number of implications, and one of them is that the debugger is simply an interpreter over activation records, because when the program is in any state where an error has happened and I've caught the error, I can have a look at the stack, and one of the errors that I can have is simply an error that halts the system, that boots me into a debugger, which it is written in Smalltalk, and then in that debugger I can step through the code, and so a traditional debugger like a C-level debugger, which displays stack frames which are on a machine stack, is replaced by an inspector for a linked list of activation records, and that's my model. So it's very nice because I can do things like implement exception search, which needs to search activation records to find a handler, just like like I do any other Smalltalk code. So exception search is not down in the VM. It's something that I can program and something that I can alter. It also means that if I want to do something like implement partial continuations, which have been used in many applications, but as nice ways of dealing with web servers, where the back button means that suddenly I've got where was I in this web page and where am I in this web page, and it would be really nice to be able to go forward, etc. It'd be really nice to deal with that by being able to take copies of the stack and remember what state I was when the user hit the back button. And activation records as objects makes it trivial to implement that kind of control structure. So it might seem exotic, but it actually has very practical applications. Now, okay, so there's a severe performance overhead, and the early Smalltalk VMs suffered from this problem of having to allocate an activation record every time we send a method. And one of the things is that if we've got activation records which are distinct objects, then the arguments that we're marshalling as we make a send in one activation have to be copied to the activation record which executes the method, whereas in stack frames the outgoing arguments become the incoming arguments on the stack, and everything's overlapped. But in implementing that inline cache, Peter Deutsch had to solve the problem of mapping this execution model to real machine instructions. And so he also solved the problem of mapping activation record objects to stack frames. So in fact, what happens in a real VM is that we can create conventional stack frames. And when the programmer asks for an activation record for the current activation, we give it an object which is kind of a proxy to the stack frame, and that's created on demand. So we don't have the overhead that you might think. But we still have the freedom in the language, even though in the VM we're not actually creating context a lot, that when we want, we have a way of accessing our current execution state from within the system as a first-class object. So the question becomes, okay, given we've got methods and a compiler and everything else and activation records, could we actually implement speculative inlining above the VM entirely in Smalltalk and have this really complicated piece of optimization technology be something that you could interactively develop while you were interacting with your program and your test cases, and be written in a garbage collected high-level language? And the answer is yes. So now the model of our system is that, on the left we have bytecoded methods which are compiled by the baseline JIT into machine code with counters. And now when those counters trip, I arrange that a message is sent back into the Smalltalk system, just like an exception arising from the runtime. And now my optimizer is a Smalltalk program, so it's a white box. And what that optimizer does is output a bytecoded method, which represents the inlining of many, many simple bytecoded methods. But since we want to get the same performance as an aggressive optimizing compiler that is targeting machine instructions, we don't want to use the abstract bytecode that only encodes for abstract operations, like the at, which is not bound. If you look at how at is actually implemented once you get to an array, then there's a primitive operation in the VM which is going to examine the object and examine the argument and make sure that everything's valid and actually yield the object. So that primitive is hairy. The receiver might be an immediate object, might be a tagged pointer, or it might be an object. And so it has to ask that question. And then it might be an array of bytes, an array of characters, it might be an array of objects, several different kinds of arrays. And so we have to dispatch on the kind of array to find out what kind of at operation is. And when we find out how the object is represented, only then can we do the bounds check, because then we know how big the elements are. And then we have to index. So you might see as many as 80 or 100 machine instructions in the implementation of the at primitive. And that's really no good. What we want to do in our optimized code is generate the one instruction or the two instructions that just fetch a given field of an object. So the way that we do that by maintaining our architecture is that we extend our bytecode set with one bytecode that can encode for unsafe operations. So this is a bytecode which is not legal for the normal compiler to generate. It's only legal for the optimizing compiler to generate once it's proved that in this particular context it's safe to use this particular instruction. And so these bytecodes, which I've done in red, code for unsafe operations like, okay, you're indexing something that looks like an array, and you can be sure that the index is a small integer that's in range. And so the JIT is free to generate just the two instructions and go ahead. And then this method is installed in some method dictionary, and the next time it's sent, the JIT is going to, baseline JIT, which has now been extended in a very simple way with support for generating these instructions, is going to generate the equivalent method. In exactly the same way, if the execution of the speculatively inline code fails one of its guards and we find out that there's more polymorphism, we're going to fail. But this time our de-optimizer is again a white box, and it can manipulate these first-class activation records to convert the one inlined optimized activation record into the the set of unoptimized things and allow the system to continue. But the advantage now is that all of that machinery that was implemented in a low-level, non-garbage collected language in a traditional VM is now available to us in a very, very powerful, concise, dynamic language. So at this point, I'd like to hand over to Clément.
Okay, so I'm going to take you through the example of how a specific method is optimized. I choose to pick this method. I hope you will be able to understand it. So this method is called display. It takes an argument which is list of drink. Eliot has already explained what the message do does. It's an iterator method that iterates over the collection, and at each iteration over the collection, the message sent display on screen is sent to the receiver self with the argument drink. So the traditional way this method will be executed on a conventional object-oriented virtual machine is as follows. So the first time the loop body is executed, the message send display on screen, the virtual machine needs to fetch which method is actually called for the specific selector, and then can cache it in the global method cache and can interpret the bytecode of the method. During the next few executions, it will keep interpreting, but will not need to fetch to perform the lookup because the lookup result is already in the cache. Then, probably around the 7th execution in our virtual machine, it's usually the 2nd or 3rd execution, the baseline JIT compiler will generate machine code for the display for the loop body. So generating machine code takes a bit of time, but the execution time of the generated method will be smaller. The machine code is decorated with inline caches, as explained Eliot, and in our case with counters. The next 1000 execution, the machine code generated by the baseline JIT compiler will be executed. Then after 1000 execution, we need to adaptively recompile the method based on the types we have met and based on the counters to generate much more efficient code. So at this step, the compilation time will be greater than the baseline JIT, but the code generated will be much faster. And so basically there is a trade-off between compilation time and execution time, and depending on the virtual machine, this is done in 2 or 3 or 4 steps for WebKit. So in our example, we will execute the method display with over 30,000 drinks. So as Eliot explained, what will happen is that at some point, the machine code version of the method, which is generated with counters and conditional branches, will detect that this method is frequently used. So we added counters and branches because we believe that based on our profiler, it induced less overhead compared to the upper method counter. So the thing is, due to our design, the method display cannot detect a hotspot because it doesn't have any branch. But the method do has the to-do method, which is similar to for in a for loop in conventional language, and it has a branch to escape the loop. So this method can actually detect a hotspot on the escaping branch. So if we execute that over 30,000 times, the virtual machine.
Why don't we say that? So what happens with the Smalltalk compiler to improve performance of a small series of selectors is that the bytecode compiler translates if then else, while true, to do, and an or into branch code. So some message, and we made the mistake of not realizing that it's implicit, but a small set of the control messages are actually compiled down to branch bytecodes. And so the way to read 1 to self-sized do is kind of, index becomes equal to 1, index less than a limit becomes equal to self-size, index less than or equal to limit while true, and the compiler is generating a conditional branch.
So the problem is that once the hotspot is detected, what can we optimize in that method? Because we have the same problem as before. There is really little that we can optimize because we still have all the virtual calls, all the message sends, like self-size, like at, like the evaluation of the closure. So one thing that costs really a lot in our runtime is the creation of closure and the evaluation of closure. So here the message value will actually evaluate the block closure, and in the outer method display we were creating a closure. So when the hotspot is detected, we have the current state of the stack. So the bottom stack frame is the stack frame with the method do, and the frame just above is the stack frame for display. So the thing that the optimizer can do is look ahead in the stack to find the best method to optimize. And it happens that because of the block evaluation, and the outer frame is creating the block, and this frame is evaluating the block. So if we are able to inline the bottom frame into the outer frame, we will be able to remove the block creation and the block evaluation. So for this purpose, the optimizer will find out that the best method to optimize is one method ahead. Another problem is that display is probably used in a user application. So it will be very specific with probably specific types and things like that. Typically, list of drinks will always be an array. The do method can be shared between multiple collections, and it's really difficult to optimize the do method if it's at the top of the hierarchy, because it will be used by so many parts of the system that there is a high chance that there will be polymorphic inside the method. So what we do is that we want to speculatively inline the message send do. So we will replace the do send by the actual method. So the way we do that is that we use type feedback. So as Eliot mentioned, with the inline caches, we can know for each send site the types we have already met for the receiver. So in our case, the optimizing compiler can know that for the 30,000 previous execution, do was sent only on an array in that specific send site. The second concept to introduce is guards. So as the optimization is speculative, we need to be able to guarantee that the speculation is always correct. So if in the future this method will be called not with an array, but with an ordered collection or a dictionary, we need to dynamically de-optimize the code to restore the unoptimized state and execute the correct version of the code. Yeah, so as the optimized method that we will generate as inline multiple method, if the guard fail, we will need to de-optimize one stack frame into multiple stack frames. So the way it works is that first we add a guard that ensures that the argument list of drinks has correctly the class array. And so I write this at the Smalltalk level as pseudocode so people can understand, but this cannot actually be expressed at Smalltalk level. It can be expressed only at bytecode and machine code level. And then we have inline the first method do. Then we realize that we are immediately creating a closure and evaluating the closure just afterwards, so we can remove the closure creation and evaluation. Finally, what we want to optimize is the access to the array. So as Eliot explained, I'm not going to go through everything again, but the accessing to an array in Smalltalk is a very expensive operation. We need to check if the index is an integer, if it's in bounds, what is the actual type of the object. So as we know right now that the list of drink has the class array, we know that an array holds actually object-oriented pointer inside. It's not a byte array, for example. We know that, and because of the loop, which iterates between 1 and the size of the array, the optimizing compiler can know that the index is always in bounds. So we are able to use an unsafe operation that directly access to the specific field of the array. Okay. So the overall optimizer architecture works as follows. So it's implemented fully in Smalltalk. it takes as input a stack which is a reified stack in the Smalltalk language, where a hotspot has been detected, and it takes as input the branch and type information that has been gathered from the inline caches and the counters from the virtual machine. What the optimizer does is to generate an optimized bytecoded method, but also dependency information. So this is because, for example, when you inline the method do, it's possible that the Smalltalk programmer would like to redefine that method, and it will change its behavior. And when this method will be redefined, we need to discard all the optimized methods that have inlined that method to recover stable state. And the last thing generated by the optimizing compiler is the optimization metadata, which is used to be able to recover the optimized stack frame from the optimized stack frame, the unoptimized stack frames. So the optimizer works as decompiling the bytecoded method into a single static assignment control flow graph, which is a classical intermediate representation for compilers. Then it does some optimization passes, and it generates bytecode, which is different from most compiler. So the decompiler works as a scanner, which needs to analyze things like jumps, like anticipate where the back jumps will target, and things like that. Then it builds a control flow graph. It does minor things like canonicalizing a loop to expect them in a specific state, and more importantly, it asks the virtual machine to provide the type annotation that were available in the inline caches. And the decompiler will annotate every virtual call node with the type annotation, so it can reuse all the type information for inlining. And then we do all the SSA transformations, adding phi nodes and things like that. So the current architecture, in the current architecture, we use mainly like 3 optimizations. So the first one is speculative inlining, as we described before. So we will add a guard to ensure that the speculation is always correct, and we will inline the method on the closure evaluation. Then we try to do some range optimization. So as shown, we do things like removing bounce check for the at method. We also remove overflow checks. So in a similar way to at, the plus operation in Smalltalk will automatically cast a small representation of integers to a representation of large integers. And if the optimizer can figure out that an overflow never happens, it does not need to do the overflow check. And lastly, and this is very important for a language like Smalltalk, we fold the constants. So what's happening is that we have many very short methods that just answer a constant, like an object check if it has a specific type or something. So lastly, and this is I think the untraditional part, we need to convert back the representation to bytecode. So this is a bit strange. The first thing we do is to convert the SSI representation to a stack-based representation. So we need to map back which value will be actually a temporary variable and which value will be spilled on stack. Then, in a similar way, we will allocate registers. We map all the temporaries to specific slots. So, for example, if we have inline multiple methods, it's possible that the same temporary multiple temporaries will share the same temporary slots in the optimized frame. And lastly, we encode the optimized method in the bytecode set. So another interesting part is about the optimization. So a typical problem that exists in a C++ virtual machine is that you need at the same time to map from the machine state, so things like which value is in the register, which value is boxed or unboxed, and also recreate at the same time a multiple stack frame for one stack frame. In our case, we have already the baseline JIT compiler that provides a reified version of the stack frame in the language. And the baseline compiler already maps the register state to stack state. It already boxes objects that were unboxed. And so the the way that the optimizer works, it has an optimized stack frame that looks like it's a method that has been executed by the bytecode interpreter. Everything is in stack and everything is object. With the optimization metadata, it's able to recreate multiple stack frame from one stack frame, and it's also able to reconstruct objects that, like for example, recreating a block closure.
Right. I mean, if you look at the example, the original example, if we were to get some pause halfway through, there's a closure that the optimizing compiler completely eliminated. And yet when we de-optimize, we have to recreate that closure. We have to imagine what it would be like and create the object so that the state is exactly the same. So the optimizing compiler is actually able to lead object creations, and the de-optimization process is quite complicated. It has to construct an exact copy of the state as it had been had the optimization never occurred.
Yeah. So about dependency management, I explained a bit before. So the problem is that in Smalltalk, we can load new code while the program is running. We can edit the method while the program is running. And if the method edited is already inline in an optimized method, that optimized method needs to be discarded. So we need to have a very strict management of the dependency for each optimized method to see if it needs to be discarded when new code is installed. So another thing that remains from our design is the hot startup. So it's possible to keep the optimized bytecoded method because they are platform independent across multiple startups.
Yeah, we should say a bit first about the Smalltalk program format. So most systems that we're talking about here, certainly JavaScript, start up from some clean state. So the problem that they have is that they start up, JavaScript programs start off with the text that's downloaded from the web server. It needs to be compiled and thing. You're starting off from a simple state. Smalltalk has quite a different architecture. Smalltalk has what's called a snapshot, which is a freezing of its heap. So what's stored on the disk is all of the objects that make up your Smalltalk system, bitmaps, but certainly class objects and methods. And when you bring up the system, you're basically just faulting in this file image of the heap into the VM, populating the heap and letting it go. So and there's the ability to snapshot the system at any point. So the programmer chooses when to save, and the snapshot process just freezes the whole heap. So what we've got in our system is, because we construct these optimized methods as normal bytecode methods, and they live in the method dictionaries in classes, we could save the system in an optimized state. So we're doing something that traditional JIT VMs just can't do. So, yeah, we needed to say that. Sorry.
Yeah. So another thing we try to build is like different tools to be able to easily debug the optimizer, because it's in Smalltalk. So to use the Smalltalk debugger, the Smalltalk inspectors, but we try to do more than that. So we try to build a tool to validate between each optimization pass that the intermediate representation is in a clean state, and that allows us to find out many bugs and to guarantee that if someone wants to contribute to an optimization pass or something, it will not crash the whole system. So what we want to do in the future is to also target double arithmetics. So right now in Smalltalk, we use a box representation of double precision floating pointer. It's fairly slow, so most developers avoid to use floating pointers in Smalltalk simply. And we want to be able to control when the virtual machine needs to box and unbox the floating pointer object to avoid extra conversions and to speed up the computation.
Yeah, go back. So the way that we do that, if you look at a Java virtual machine and Java bytecode, Java has in it the notion of some of the bytecodes accessing the object representation in a method, and some of the bytecodes specifying unboxed floating point operations. So the abstract model of a Java stack is some part of it is object pointers and some part of it is flat data. And some of the bytecodes access that flat byte data, performing floating point operations or other unboxed operations. And some of the bytecodes access the object part of the stack doing things like virtual calls, et cetera, et cetera. So if we enrich our model of the activation record so that we have a byte array in it that can hold the flat data, we can add unsafe bytecode operations that do floating point operations on that byte array. So we have an abstract model of how it's executed, and indeed in the interpreter part, if we were in Smalltalk in the debugger stepping through those bytecodes, though that is actually what would happen. But our optimizing compiler, the baseline JIT has the job of mapping that byte array down onto the floating point registers and converting those bytecodes that address the byte array into instructions on the floating point register state. And so that's an interesting example of how in our layered architecture, as was mentioned in the introduction, we have this separation of concerns where the base level JIT has the job of mapping machine registers to stack slots. And then the higher level of the system has the job of mapping the stack slots back to the abstract execution state. And this dynamic de-optimization process, which is quite complicated, poses problems in systems that are not so layered, and is mentioned in the literature as a problem area. And in our double layer system, the computation is simpler because it's been split into two levels. So that's it. And to say a little bit more about the project, Clément is a PhD student at INRIA, French lab in Lille in northern France. I've been a Smalltalk implementer for a long time. I'm employed at Cadence and semi-independent. And the virtual machine that we have, which is called COG, is open source. There's a website where you can find out about it. If you're interested in finding out more about the system or even using it for projects or collaborating, please get in touch with us in email or the virtual machine development list that's at the bottom in the Squeak community is used to discuss the virtual machine, which is used in a number of systems, Smalltalk dialects like Faro, Squeak, and Quis, but also the Newspeak modular Smalltalk system designed by Gilad Bracha of the Java specification fame. So we hope we can interest some of you into coming and getting further involved, because we offer a context in which the development of an optimizing compiler is something done in a very high level language. Something we didn't have time to touch on here is that indeed the base level JIT, the lower parts of the system, is also a Smalltalk program. And that's developed interactively as a simulator, and it's something that is converted to C and then compiled to form our production VM. But during development, as we're developing that JIT, including the implementation of those unsafe bytecodes and the things like the floating point arithmetic stuff that we hope to do soon, that's again implemented in a high level language and has an interactive development experience. Even though it punches out a fixed VM. Well, we've got 1 minute left. I think we should stop there.
So, you touched on this repeatedly, sort of the Java approach and the Smalltalk approach, and this has been a war, not a war, but a distinction. The IBM 38.
It's a schism. It's a schism.
There was the Lisp machine view of the world, and there was the C view of the world. And JavaScript is sort of on the C side.
Java.
Well, but JavaScript too, because it's sort of, you don't ever save anything and accumulate something.
Right.
The whole snapshot notion.
Right.
Programs don't get faster, they're as fast as they'll ever be.
Yes.
Which was actually the argument for workstations, is that they're always as fast as they're going to be. They don't get faster at night, which meant they were never fast enough until they were. This social stuff, is that playing out in any interesting way? Or the JavaScript people rediscovering the world? Are they?
It's certainly true. If you trace the personnel, it's quite interesting. Peter Deutsch's work inspired the Self team of Dave Unger and Urs Hersley, and Urs was contacted by some people who thought that there was the prospect of implementing fast Smalltalk virtual machines remuneratively for Wall Street. Turns out that Smalltalk is used in the financial industry a lot because financial domains evolve very quickly because of the legislative environment, and dynamically typed, untyped languages are one of the few languages where the rate of development can keep up with the rate of development of the real world. So they thought that there was the potential of making a big profit if they could apply this technology to Smalltalk, and that Urs joined up with a very, very able programmer called Lars Bak to do what was called Strongtalk, the Strongtalk VM. And there was a bidding war because while they were producing Strongtalk, they could see that Java had just arrived. This is now mid-90s. And they decided to do a Java VM at the same time that they did a Smalltalk VM. And indeed, it was Sun that bought Java. They had deeper pockets than the Smalltalk community. And so that technology, which started off Smalltalk and Self, realized itself in Java first from Sun. And then later on, Lars went to Google to speed up JavaScript, because JavaScript was so important. And his VM, the first VM, is called V8. And internally, that VM recreates a lot of Smalltalk runtime properties to allow it to apply these techniques. So in the JavaScript model, we only have double precision numbers, and notionally we would either box, or we would do that fantastic trick from old Lisp machines where objects are not a numbers, and so everything's a number, and you just use the small part of the address space with the 53 bits of mantissa, and you're not a number indicator to actually address objects. So that's one way of doing it, or the other way of doing it, which is in V8, is where you do indeed have box doubles, but if the system, as it's compiling text or producing results, finds out that the result is actually representable as an integer, it will use a tag pointer, just like in Smalltalk. So internally, doubles are used infrequently, and integers are used as much as possible, and maps are created that correspond to classes. Maps define the layout of a particular object as a sequence of slots that only has a subset of all of the properties that it might have, etc. And so all of that machinery came from Smalltalk and has been reproduced internally inside the VM. So these VMs are quite recognizable. So there's that hidden way in which the technology has been recovered. But that really comes to the schism, because what the community that's unaware of the VM technology is proposing is the right way to deal with this dynamism is to add things like final, where we can declare a class as something that can't have subclasses, and therefore we know that nothing will be overridden, and therefore we can, and the virtual machine community knows that way just doesn't buy you anything. You can do that automatically, and so why bother? So I don't want to say more than I think it's very, very difficult to communicate this information to the broader community. It's not obvious stuff, and we haven't necessarily done a good job even of talking to language designers, because people are still proposing adding statifiers to dynamic languages, whereas I think that the state of the compiling of compiling for dynamic languages, while it's not reached exactly the same performance, is still increasing and catching up to static compilers and still has a lot of future.
You also mentioned sort of a secret message that a lot of languages are alive where there's lots of money that people just don't think about. I keep finding out about new ones. I thought I knew all, I thought I knew all the old languages.
Yes.
APL's still alive, and
yes, hugely. Yeah.
People are inventing new APLs.
Yeah. And in fact, just a few days ago, we were visiting Lam Research in the East Bay. We have a relationship with them. They are one of the world's leading producers of chip manufacturing machines. They build these huge machines which are full of things which, for example, one of the things that these machines might be full of is a two-step gas. So what's a two-step gas? A two-step gas is a gas which, if you inhale it, you will walk 2 steps before you drop dead. That's what a two-step gas is. Right, so these machines are very, very interesting. There's an incredibly sophisticated use of surface physics, etc. But there's some impressive industrial robotics going on, moving these wafers from machine to machine. You might have as many as 200 steps in 200 separate machines in the production of a chip, as many as 70 days to produce a chip. All of that control technology is done in Smalltalk. It was a DoD financed, a DARPA financed project in the 90s that produced a system called ControlWorks, and probably every smartphone on the planet was at some time going through a machine that was controlled by Smalltalk. So these apparently hidden old languages are used in very, very important ways, and we just don't hear about them.
Scheme still uses in strange places too.
Yes.
We call it in this country, we call them one whiff. You get one whiff and then you keel over. Yeah, no, they're real serious.
Yeah.
Okay. Well, thank you.
Thank you.